Hello. So in today's video, we're going to be going over a couple of questions from the mass energy problem set and the standard model problem set. So to begin, we have question 11 of the mass energy. In this question, we have to convert between the universal mass unit and the mega electron volts. So rather than using E equals mc squared, we're going to jump right into the conversion factor, which is found on the reference table. So the universal mass unit, one universal mass units equals 931 mega electron volts. So to do this math, we're just going to take the 9.06 times 10 to the minus 3, and we're going to multiply that by cat I. Okay. We have to go now. Okay, sorry about that. Okay, and multiply that by the 931 mega electron volts. This is in universal mass units. When you do that math out, when you multiply the two, you get choice 3. So that's pretty much how you do these types of questions. You just have to do the quick conversion rather than worrying about switching it into kilograms and then converting it using E equals mc squared. It's just much faster this way. This next question works the same way. It's asking to find the mega electron volts of lithium. They give you the mass of lithium, and just like before, just like before, you're just going to simply multiply the two together times the 931. And when you do that, you get 6,531 mega electron volts. That's pretty much how those questions go. I think they're pretty straightforward. Now, this next set of questions that we have, you can just ignore this, just stayed over. Oh, there it goes. This next set of questions that we have is a type of question that we haven't actually seen before. This is usually taught in the electricity unit, but obviously we haven't done that yet. So we're just going to have to learn it right now. And that is the charge of our different particles. So if you remember from chemistry, the unit for charge that you most often used was just the elementary charge. Protons have +1, electrons have -1. And just like all the other non-standard SI units, there's a very good reason why we use those. It's very convenient to talk about them. However, we often have to convert them into the proper SI units to do calculations. In this case, the SI unit for charge is the coulomb, given by the capital C over here. So we're going to need to convert from our elementary charges into our coulombs for the next 3 problems. So we're looking at an anti-strange quark, and if you look on your reference table, you can see that the charge of a normal strange quark is 1/3 of an elementary charge. An anti-strange quark would have a positive charge for that. So we have a +1/3 charge times the conversion factor. The conversion factor is found over here. It may look very familiar to you. It's that 1.6 times 10 to the minus 19 coulombs. And when you do that math out, you're going to get the positive 5.33 times 10 to the minus 23rd coulombs. That's how that question works. All right, next one, very, very similar. We're looking at an antiproton. A proton usually has a +1 charge, but because this is an antiproton, it's going to have a -1 charge. So it's just going to be -1 times 1.6 times 10 to the minus 19 coulombs, which is the negative 1.6 times 10 to the minus 19 coulombs. And that is our value that we have here. Pretty straightforward. Now, this next set of questions, again, is something that's key for the electricity unit. How these questions work is a subatomic particle, so this is not a quark, but the things that make quarks make up, has to have a whole number charge. And what I mean by that is the charges need to be something like -1 or 0 or 1 or 2 or 3 or something like that. It has to be a whole number. It can't be any fraction of that. So in elementary charges, it needs to be a whole number, but since we're talking about coulombs, here, it needs to be a value that's divisible by 1.6 times 10 to the minus 19. So in these type of questions where you're asked what's possible to have a charge, you just need to take your values and divide it by the 1.6 times 10 to the minus 19 and see if you get a whole number back. Basically what you're doing is you're converting it into elementary charges and you're seeing, is this a whole number or not? Because you can't have part of a proton, you can't have part of an electron. You either have the charge or you don't. Now, I know quarks is now thrown into this mix where usually when I teach this, it isn't at this point. But when we're talking about subatomic particles, we're not talking about quarks. We're talking about the things that quarks can make up, or in the case of leptons, just fundamental particles like the electron. So you just need to take your values divided by 1.6. Anything smaller than times 10 to the 19 definitely won't do. If you take 5 times 10 to the 19 divided by 1.6, you don't get a whole number, but you do for 3.2 times 10 to the minus 19 is just 2. So it's a whole number, so it's possible for that to happen. That's pretty much it. I hope this was helpful, and have a good one.